And there are different kind of correlation. Like for example, you may heard about the Pearson correlation. And Pearson correlation is basically the correlation between the scale variables, and it is the correlation which you found most of the time in literature. Then after that, we are having the correlation between ordinal variables. The correlation between ordinal variables is known as rank correlation, and there are two measures of rank correlations. One is Spearman correlation, and second is Kendall-Tau correlation. Then after Pearson correlation, rank correlation, we are having one more type of correlation that is called partial correlation. So partial correlation is also very important concept in the statistics. And after the partial correlation, then we have a concept called multiple correlation. So these are the different type of correlation in statistics, and we are going to discuss all of them, I think, in much detail. So first of all, I'm going to explain the concept of correlation. So for the concept, I'm taking one example, and the example is, suppose there are two variables. One variable is X variable, and second variable is Y variable. And let's say the unit of X is meter, and the unit of X is kg. And we want to see, is there any relationship between X and Y? And these are the just hypothetical variables, and I'm taking hypothetical units just to explain the concept. So let's take the 5 values of X and the 5 values of Y. So let's say the value of X is 3, 4, 3, 5, 4. So I take the 5 values of X, and similarly I will take 7, 8, 8, 9, 7. So 5 values of X and 5 values of Y. And assume that the mean of X is 4 and mean of X is 7. So this is called X bar and this is called Y bar. This is just assumption. So let's assume that the mean of X is 4 and the mean of Y is 7. After that, we calculate one thing. This is called dx, which is nothing but X minus X bar. So this concept is known as that how much the observation of X are different from the mean or are away from the mean. Like 3 minus 4. So we can write here 3 minus 4, 4 minus 4, 3 minus 4, 5 minus 4, and 4 minus 4, right? So we are getting the answer like minus 1 and 0, minus 1, 1, and 4 minus 4 is 0. So it means these are the values which are away from the mean. Similarly, we can calculate the dy, which is y minus y bar. So the mean of y is 7. So I will calculate this 7 minus 7 is equal to 0. Then 8 minus 7, this is 8 minus 7 is 1. 8 minus 7 is 1. 9 minus 7 is 2. And 7 minus 7 is 0. Okay, so this is hypothetical, so don't worry about that. And this is sum of dx, and this is the sum of dy. Now after that, I will calculate one more thing, which is known as dx multiplied by dy, or we can write this as x minus x bar and y minus y bar. Now this multiplication has two sides, two effects. One is known as sign effect, and second effect is known as effect size. So we call it effect size. Now if I do for this, so you can see the sign is 0 and effect size is also 0. In no, sorry, we have to multiply it. Okay, now multiply with dx. This is minus 1 multiplied by 0, but anything which is multiplied by 0 is 0, and this is the effect is also 0. So 0 multiplied by 0 also 0, 0. Now in this case, when we multiply with minus into plus, so the answer is minus. So we can say the both are opposite to each other. One is less than the mean and other is more than the mean, and the effect is 1. Similarly, 1 multiplied by 2, this is dx multiplied by dy. The sign is positive because positive multiplied by positive is positive, and the effect is 2. Similarly, 0. Now we find out the overall value here. We just calculate sigma dx dy, and this total value again have two important things. One is what is the sign and what is the value, right? So two things are very important here. If the sign of dx dy is positive, so we can say positive relationship is there, and if the sign is negative, then we can say there is a negative relationship between the x and y, and this dy upon dx value is unstandardized. This is a problem here. So from this dx dy we generate one very important formula, and that formula is known as covariance. So I am showing you how we can define covariance from here. So let me delete this and showing the covariance to you. Now this I'm writing a formula that covariance between x and y is equal to sigma dx multiply dy upon n minus 1. So this is the formula for covariance between x and y. And let's write again this dx into dy. So this is the formula for covariance. We can also write that sigma x minus x bar upon y minus y bar upon n minus 1. Now I'm asking you one thing simple. What is the unit of the covariance here? So if you apply your common sense, just give me the answer that what is the unit of covariance here. So is there any unit of the covariance? If yes, if no, why? If yes, what is the unit? So this is my question. Just apply your common sense and tell me what is the unit of this covariance between x and y. The unit of x is meter and the unit of y is kilogram. So this is the issue. Now, what is the unit of? Okay, so all of you are saying that there is no unit, no unit, no unit. But I don't know why you are saying this, because if you just apply your common sense, the x minus x bar is represented in the meter and y minus y bar is represented in the kilogram. So the unit of covariance between x and y is the unit of x multiplied by unit of y. So the unit of covariance is meter into kg. So meter kg. This is the unit of meter into kg, right? Now again, my second question is that if I change the meter into centimeter, if I change the kilogram into pound, so do you think the value of covariance will change or not? If I change the unit of x and y, now I am expressing x in centimeter, and now I am expressing the y in not kilogram, rather pound. So after making this change, do you think this value, the value of covariance, will change or not? So here you are also wrong. The value of covariance will also change. The covariance, the value will also change. So the biggest problem with covariance is that its value depends upon the unit of x and y, right? So I should write here the major problem of covariance between x and y is equal to sigma dx dy, and this is the n minus 1. So problem number 1, this is unstandardized. This is not standardized. Why it is not standardized? Because the covariance between x and y depends upon the unit of x and the unit of y, right? So this is the biggest problem in covariance. For example, I'm saying that the covariance between x and y is 2000. of covariance between A and B is 500. Covariance between P and Q is 6. Right. So can you conclude which covariance is high, which covariance is low? This is 200, 6, and 5. The problem is that the covariance value depends upon the unit. So by looking at the covariance between X and Y, we can only conclude that because all the values are positive, so there may be positive correlation between X and Y, or A and B, or P and Q. If I put minus here, so you can only say that A and B are negatively related, and X and Y are positively related, and P and Q are positively related. But you cannot tell me that whether the correlation is strong, whether the correlation is low, whether the correlation is moderate, whether the correlation is significant, whether the correlation is insignificant. You can't tell. So actually, we cannot decide whether the relationship between X and Y is significant or not using the covariance. We cannot say whether the relationship between X and Y is very high, very low, moderate. So this is the problem of covariance. So I just write one sentence. The covariance between X and Y is just an unstandardized measure of relationship. So we want some solution for that. So therefore, covariance is not used in most of the analysis. It's just an indication, and it is the use of covariance in hardly few cases. Right? In very few cases, we plot the covariance and variance matrix. That is used in very rarely in some of the statistics. More than 90% of the cases, you have to find out what correlation. Now, the problem with covariance is that it is unstandardized. So we want what we want. We want to make it unitless, to make it standardized. So we want to make the covariance unitless, to make it standardized. So this is the objective of, right? And now how can we do that? So let's see. Now we know that the covariance is equal to sigma x minus x bar upon y minus y bar, and this is n minus 1. So the unit of covariance is meter and kg. So if I divide it by standard deviation of x and standard deviation of y, so the unit of x is divided by unit of x here, unit of y is divided by unit of y here. So now it is a unitless, right? It is now it is a unitless. So this unitless value is called r xy. So r xy, right? So now this is the genesis of correlation. So in this way, correlation developed, and the person who gave this formula is known as Carl Pearson. The professor Carl Pearson gave this formula, and the exact. So there are many varieties of correlation, like r xy. In many books, you can see that it is nothing. It is a covariance between x and y upon standard deviation of x upon standard deviation of y. Then we are having this formula also. If we open this value, then we can say sigma x minus x bar y minus y bar. This is the covariance n minus 1. Then you know that the standard deviation of x is sigma x minus x bar whole square upon n minus 1. Similarly, the value of standard deviation of y is sigma y minus y bar upon n minus 1, right? So because n minus 1, n minus 1, n minus, you can take common and cancel. So this is the formula for the correlation between x and y. So in this way, we came out with the formula for correlation, and it is a unit-free measure of relationship. This correlation is known as standardized measure of relationship. So we can write one conclusion here, that correlation is the standardized and unit-free measure of relationship between two variables. So I note it down. The correlation between x and y is an standard is a unit free. It is a unit free measure of the relationship between the relationship between two scale variables. We can calculate correlation between two scale variables, that is x and y. So now you must have understood that what is the difference between correlation and the covariance. And covariance is just the unstandardized measure of relationship between the two scale variables, and correlation is a standardized measure of relationship between the two variables. Now, some basic things about the correlation. Now, features of correlation. The features of correlation, which you must know. Number one, it always comes between -1 and 1. It always lies between -1 to +1. And this -1 to +1 is divided into many regions. Like this is -1, this is +1, and this is 0. So this case, when correlation is -1, this correlation is known as perfect negative correlation. Perfect negative correlation. This correlation is known as perfect negative correlation. And this case R is equal to +1 is known as perfect positive correlation. Perfect positive correlation. And this value is known as no correlation. And further, we divide this range also. This is approximately 4.5. This is 7, and this is 1. So this part is known as low correlation. This part is known as moderate correlation, and this part is known as strong correlation. Right? Similarly, here also. So we are having three types of correlation: low correlation or no correlation, moderate correlation, strong correlation, perfect positive correlation, perfect negative correlation. So on the basis of the value of R, we can decide what is the strength of the correlation. So as I said, that correlation is a standardized measure of relationship. So if we look at the value of R, we can decide very easily. So whether the correlation is strong, whether the correlation is weak, whether the correlation is moderate. So this is the benefit of correlation. It gives you a standardized measure of relationship. Okay, so this is the first property of correlation. Now, second property. The second property of correlation is that if you plot the correlation, this is upward sloping correlation. There may be downward sloping correlation, and there may be this line. So this upward sloping correlation, the line indicates the positive correlation. This downward is negative correlation. And when x changes, but there is no change in y, then this is simply the no correlation. So this is the kind of graph you will have if you plot the correlation between x and y. So sometimes we plot this scatter plot, and this scatter plot will give you the idea that whether the correlation is positive, negative, or 0. Then third property of correlation is that whenever we analyze the correlation, so there are three steps. There are the three steps of correlation analysis. So in first step, we identify whether the correlation is significant or not. So first step is that whether the correlation is significant or not. So this is the first point. Second point, that what is the direction of the correlation? What is the direction of the correlation? It is positive or it is negative. You can see the direction only when correlation is significant, otherwise there is no meaning of the direction. If it is insignificant, if the correlation is insignificant, it means you cannot say it is positive or negative, it is just insignificant, 0. The third case we have to check is the effect size. Effect size, or this is in simple language, it is known as strength. What is the strength of the correlation? So as I said that 0 between 0 plus minus 4.5, you can say it is a low correlation, and 4.5 plus minus 4.5 to 7, it is moderate correlation, and greater than 7 plus minus 7, it is called strong correlation. So this concept you have to understand that whenever we analyze the correlation analysis, we have to find out three things: whether it is significant or not, what is the direction of the correlation, and what is the strength of the correlation. So these three informations are required after the correlation analysis. Okay, so now I'm showing you that how to analyze the correlation in SPSS. So I'm going to open a file to apply the correlation. And one thing which I also want to describe here before moving to the SPSS, that the fourth point is the correlation can be applicable only between the two variables. So it is applicable only between two scale variables. If you have three scale variables, it will make the pair, right? So that is a problem actually. So this is one of the problem of correlation analysis. You can calculate the correlation between two variables. You cannot calculate the correlation between three variables. So that is a problem. And fifth point is that there is another concept which is known as causation, right? So causation means correlation should be applicable only when there is a logical causation between them. Like for example, if you calculate the correlation between your height and age of a tree, or temperature of let's say temperature of India and corona diseases in US, right? So there is no logical connection between these variables. So there must be some logical connection between the variables, otherwise there is no point of calculating the correlation, right? If I want to calculate the correlation between, let's say, the temperature and the stock market, right? So if I want to predict the stock market on the basis of the temperature, right? So because there is no logical connection between the temperature and the stock market, so correlation should not be calculated between them. So there should be some logical relationship between the variables, otherwise there is no point in calculating the correlation. So this we should also remember. Now I am going to the SPSS and show you the how we can calculate the correlation. Okay,